Welcome to Saini Alloys, a trusted name in precision casting since 1999. Located in Sikandrabad, UP, we specialize in delivering high quality casting for sponge iron, cement, steel plants, hydro energy sector, and sugar industry. With over 25 years of expertise, we manufacture massive castings such as kiln tires, girth gears, riding wheels, mill head, support rollers, rolling mill chocks, machine bodies, and sprocket, etc. Our commitment to quality and precision means every casting meets or exceeds industry standards. We provide customized solutions, working closely with clients to create unique and complex parts tailored to their needs. At Saini Alloys, we do not just create casting, we build trust and long-term partnership. We always maintain a minimum inventory stock of 1 month to keep production running smoothly. This buffers helps prevent delays due to supply chain disruption, unexpected demand spikes, or material shortages. When it comes to producing large and heavy industrial components, pit molding stands out as a reliable and time-tested method, especially in India. This traditional yet effective process is widely used for manufacturing massive castings, such as kiln tires, riding wheels, rollers, girth gears, and machine bodies, which are crucial in sponge iron plants and cement industries. Number 1 step: pit formation and preparation. The process begins by digging a pit into the foundry floor, large enough to accommodate the required casting. To stabilize the structure and prevent the pit walls from collapsing, they are lined with bricks or concrete. At the bottom, a layer of cinder is laid down. This isn't just a filler. It plays an important role by allowing gases to escape during casting, reducing the risk of defects. Step 2. Molding with patterns. Next comes the shaping stage, where patterns help define the final casting form. The sweep pattern is ideal for large symmetrical parts. It uses a rotating wooden sweep board to shape the mold. The segmental pattern is commonly used for circular components like wheel rims, gear blanks, and rolling mill chocks created in segments and assembled. Step number 3. Sodium silicate molding process. For more precise and durable molds, the sodium silicate process is widely adopted. Sodium silicate acts as a binder, keeping the sand grains tightly packed. When exposed to carbon dioxide, it hardens rapidly, forming a strong, stable mold. This technique is particularly beneficial for maintaining mold shape during the pouring of molten metal. Step number 4. Cope and venting. Once the mold is set, a cope flask is placed on top with openings for pouring channels, sprues, and risers. Vent pipes are also installed, allowing gases to escape during the pour, which is critical for preventing casting defects. Coming on to the advantages of pit molding and sodium silicate. This process offers several clear benefits. Number 1. High precision and dimensional accuracy. Number 2. Cost effective for large scale castings. Number 3. Compatible with both ferrous and non-ferrous metals. Number 4. Perfect for high volume industrial production. Whether it's kiln components or massive machine bodies, pit molding ensures strength, stability, and cost efficiency. Thanks to its ability to produce large and complex geometries with accuracy, it remains a go-to choice for heavy industries around the world. Ladle heating and assembly. Proper ladle preparation is vital for smooth metal pouring. First, preheat all ladles using an oil or gas-fired ladle preheater. Heat them to 700 degrees Celsius and confirm with the laser gun. Then, heat the stopper rod assembly in an electric oven and keep it upright for handling. To check nozzle security, drop fine sand. If none leaks, it's sealed. Finally, reheat the ladle to 700 degrees Celsius and heat the nozzle with a torch before tapping to avoid clogging. Now we will walk you through one of the most critical stages of casting, melting using an induction furnace. From charging raw materials to precision pouring, every step is executed with technical expertise to ensure consistency, quality, and customer satisfaction. An induction furnace operates on the principle of electromagnetic induction. A high-frequency alternating current passes through a copper coil, generating a rapidly changing magnetic field. When metal scrap is placed inside the crucible, surrounded by this coil, eddy currents are induced in the metal, creating intense heat which melts the charge without direct contact. This clean, energy-efficient and controlled process is ideal for producing both ferrous and non-ferrous castings with tight metallurgical control. Next, The process begins with charging the furnace. Using an electromagnet, we load selected low-carbon mild steel scrap along with small quantities of ferrosilicon and coke to prevent early-stage oxidation. To ensure safety and melting speed, only clean, rust-free, oil-free, heavy melting scrap is used. Containers, whether full or empty, are strictly prohibited on the platform. The charging process is completed in about 10 to 12 rounds and each charge is recorded for accuracy. Next, once charged, the melting begins. Initially, low current is applied for 8 to 10 minutes. As the scrap transitions into a molten state, full power is used. Continuous manual or mechanical pushing ensures the scrap stays within the coil magnetic field, allowing faster and even melting. At 3/4 of the crucible height, an opening sample is taken for spectrometric analysis. We monitor the temperature at this stage, maintaining it between 1550 degrees Celsius to 1570 degrees Celsius. If carbon or silicon needs adjusting, it is done very cautiously. Additions are minimal to avoid oxidation. Slag is regularly removed to prevent overheating and contamination. Next comes the process of refining and adjustments. If the opening chemistry shows high carbon or phosphorus, we use CRC sheets to refine and reduce the composition. Before final adjustments, we take a second oxidation sample and perlite ore is used to bind and remove any remaining slag. Maintaining the right temperature is crucial to protect the crucible lining. If temperature rises above acceptable limits, we either add scrap or reduce current. This maintains furnace longevity and ensures metal quality. Next is final alloying and tapping. Once the melt is refined, ferroalloys like aluminium ingots, ferroaluminium, ferrotitanium, and ferrosilicon calcium are added in the ladle for deoxidation and grain refinement. Tapping begins at 1630 degrees Celsius to 1645 degrees Celsius into multiple ladles with argon gas purging. A final spectrometric sample is taken to confirm the melt's chemistry before pouring. We use Redex to maintain ladle temperature and reduce heat loss. Next is the pouring process. At Saini Alloys, due to the large size of our castings, multiple ladles are used to pour simultaneously. Before pouring, all ladles are manually centered and fastened over the respective sprues. Once ready, the nozzles are opened and molten metal flows into the mold cavity. The metal is poured steadily. When it reaches the base of the riser, flow is slowed down. Anti-piping compounds are added to keep the riser metal hot longer, ensuring proper feeding and shrinkage control. Pouring continues till the meniscus reaches riser height. Maintaining proper pouring rate and temperature is very essential in order to avoid casting defects. These defects could be like cold shuts, turbulence, and incomplete fills. Through this rigorous process control, skilled supervision, and precise instrumentation, our melting process operation guarantees top quality castings every time at Saini Alloys. Thank you everyone for watching the process that involves such rigorous process controlled under skilled supervision. Here we combine tradition with technology to deliver excellence in every pour. Next is risers cutting. Once the casting has completely cooled and solidified, The next step is removing the risers. This is done using oxy-gas cutting, a precise and effective method where a high-temperature flame cuts through the excess metal after homogenization. This process ensures clean separation without damaging the main body of the casting. Next is fettling and heat treatment. Fettling is the essential post-casting process that removes unwanted material like gates, risers, screws and cores, followed by cleaning and inspection. Step number 1. Knockout and decoring. Once cooled, the mold is broken to extract the casting. This is the knockout process. Internal sand cores are removed to clear all cavities. Removing excess material is step number 2. Gates and risers are removed using tools like flame cutters, pneumatic chisels, or fettle arc machines, depending on the casting's size and complexity. Step 3. Surface cleaning. Large castings are cleaned with sandblasting. Grinding and linishing smooth the surface for inspection. Step number 4. Inspection and repair. Defects like porosity, misruns, or hot tears are identified visually and fixed by welding, grinding, or patching. Now comes heat treatment, starting with normalizing. The casting is heated to 880 to 930 degrees Celsius, held to form uniform austenite, then cooled in still air. This refines the grain structure into fine pearlite or pearlite ferrite, improving toughness, ductility, and machinability. The key steps are: heat at 60 to 80 degrees Celsius per hour, soak for 1 hour per 25 mm thickness, cool in air to 600 to 700 degrees Celsius, unload based on grade, example IS 1030 at 250 to 300 degrees Celsius. This entire cycle ensures the casting meets performance and quality standards. Hardness testing confirms if heat treatment was successful. Perfect hardness means the metal has the right microstructure for strength and durability. Destructive testing plays a vital role in ensuring the quality and reliability of cast metal products. Through mechanical testing, foundries verify critical properties like strength, hardness, impact resistance, elongation, and fracture toughness. These tests confirm whether the casting meets its performance requirement and reveal any hidden defects that could affect integrity. By simulating real-world conditions, destructive testing helps prevent failures and ensures long-term durability. It's not just a step in the process. It's a commitment to delivering castings that meet the highest standards and satisfy customer expectations. That is why destructive testing is also known as the commitment to quality. In precision machining, not all machines can handle large complex components. That's why Saini Alloys invested in the Skoda horizontal boring machine, a game changer in heavy-duty machining. It handles large heavy parts standard machine can't. It is versatile, capable of boring, threading, phasing, and milling all in one. Its horizontal orientation ensures high precision and stability. Built for deep bores and rough machining, it delivers heavy-duty performance. While not CNC, it offers cost-effective production for high-volume needs. Trusted for machining gearboxes, headstocks, and rolling mill chocks, it is ideal for industrial use. With skilled operators, Skoda delivers efficiency, accuracy, and durability, making it an essential tool in precision machining. In metal casting, quality and integrity are everything. But how do we detect hidden defects without damaging the product? The answer is NDT, non-destructive testing. NDT detects internal and surface flaws like cracks, voids, inclusions, and prevents faulty parts from moving forward, ensuring strength, durability, and safety. Let's look at key NDT methods. Visual inspection, first line of defense. Liquid penetrant testing, finds surface cracks. Magnetic particle testing, detects subsurface flaws up to 5 mm. Radiography, reveals deep internal defects. Ultrasonic testing, uses sound waves for deep flaw detection. Eddy current testing, perfect for conductive materials. And pressure testing, ensure leak-proof castings. Thank you for watching our video. We appreciate your time and look forward to serving you again. Stay tuned for more updates.